Okay, hello everybody. Thank you so much for being here and welcome to the final SCRIBO seminar of this academic year. It has been a long journey during a difficult year, and we have collected, since we first started in 2020, more than 20 online seminars on Zoom. This is our 24th SCRIBO seminar, I think. And what an honor it is to introduce the INSCRIBE team today. It is my pride and my joy to be directing a group of talented, enthusiastic researchers, but not just researchers, thinkers too, who happen to be great human beings as well. And inscribers, show yourselves. I can see you in your videos. Let me introduce them one by one. Barbara Montecchi, Miguel Valerio, Roberta Ravanelli, Michele Corazza, Andrea Santamaria, Lorenzo Lassilla, and a new member, Mattia Cartolano, who's joining us today for the first time, plus our MA students, Amanda Puloma, Andrea Filippo Schimenti, Ornella Auriemma, Maria Streccioni. Today, you will see some of the INSCRIBE team in action, not the whole of it, and not me. They will be presenting our work on the mathematical values of the linear A fractions. We published our results late last year in the Journal of Archaeological Science. And right now the article is one of the most downloaded ones from the website. So huge success for us, and we're really happy. And you can read it and download it for free since it's in open access. As you know by now, INSCRIBE, Invention of Scripts and Their Beginnings, is an ESC project funded by the European Commission, based at the Alma Mater Studiorum, the University of Bologna. And it is a multidisciplinary project on the invention of writing and the ancient undeciphered scripts. Today, you will get a taste of what we try to do using several strands of research and different methods. And the linear A fractions and their values, which have been long debated in the scholarship for more than a century, will be our focus. Today, we propose a new way of looking at them using paleography, typology, constraint programming, and structural analysis. Our presenters will be Dr. Barbara Montecchi and Dr. Miguel Valerio, who are junior assistant professors in Aegean studies. They're both archaeologists and philologists. And soon to be Dr. Michele Corazza, PhD student in neural networks and all things computational. We will be joined by Professor Fabio Tamburini, full professor in linguistics and computer science at the Alma Mater, who has been truly our guide in this article. Let's welcome them. And on a personal note, let me just say that my connection is really bad, so if I crash, you can reconnect using the same link. But on a very personal note, it is a delight to be concluding the SCRIBO series this way. It's been a success through and through. We saw the participation of great scholars, and we have always had great debates, happy discussions, and new ways of looking at ancient scripts. It truly has been a joy for me and for the whole of the team. Last but not least, thank you to this great team who make my day truly every day. Thank you, guys. And thank you everybody for being here. We can start the dances. Barbara, over to you. Viva INSCRIBE, and lovely to see you all here.
Thank you, Silvia, for this lovely introduction and lovely words, and good evening to everybody. Today, we will be presenting the result of a multi-threaded paleographical, computational, typological, and statistical method applied to the linear A fraction science with the aim of shed light on their mathematical values. Before entering the topic, it is useful to briefly introduce the writing systems used in the Aegean during the Bronze Age, that is, during the second millennium BC, namely Cretan hieroglyphic, linear A, and linear B, and the signs used for numerical notations in each of these scripts. The similarity among the repertoires shows that linear B derived from linear A and linear A was adapted from Cretan hieroglyphic, although their periods of use partially overlap. Linear B is a syllabic system that registers an early phase of ancient Greek called Mycenaean Greek. Linear A has not been deciphered yet, and we do not know what language it encodes. But from the similarities in its use with linear B, we can deduce that it is also a syllabic system that mainly registers open syllables and vowels. You can see linear A syllabic signs on this slide to the left. Cretan hieroglyphic is far less clear. Some scholars believe it is also a syllabic system of the same type as linear A, but the role played by logograms in this script should be further investigated. However, all the three systems use logograms to record commodities instead of spelling them out. On this slide to the right, you see a selection of linear A logograms with interpretations based on the well-known linear logograms. I should say that, however, that some of them are uncertain, some of these interpretations. As for numerical notations, all the three Aegean scripts employ a decimal system. As shown in this slide, units are written with vertical strokes, 10 with horizontal strokes or dots, hundreds with circles. In Cretan hieroglyphic, oblique strokes are also employed for hundreds, and thousands with circles surrounded by strokes. In linear B, the sign for 10,000 is also attested. The system is cumulative and additive, and numbers are written from left to right with the powers in descending order. For example, on this linear A tablets fragment, we recognize a syllabic group by applying linear B values. We can read it as Kuro, followed by number 129, written with one circle for 100, 2 horizontal strokes for 20, and 9 vertical strokes for 9. Unlike linear B, Cretan hieroglyphic and linear A also include a set of specific signs that stand for fractional numbers. In linear A, 17 signs for fractions are attested. You see them to the left, some of which have the same shape as Cretan hieroglyphic fractions. You can see them to the right. We will now focus on linear A fractions. They are transcribed via capital letters, A, B, D, E, F, H, and so on, as you see on the slide. Signs conventionally transcribed as L2, L3, L4, L6 have numbers because they consist of a basic semicircular or triangular shape called L, to which 2, 3, 4, or 6 strokes, or sometimes reduced to dots, are added. In other words, they constitute a series. Fraction signs are mainly attested on records of commodities. In the next slide, you can see some examples. These commodities are expressed using logograms. It is important to stress that when the commodity is not be counted, but rather to be measured, as for example, agricultural commodities like cereals, figs, wine, and so on, the logogram also implicitly indicates the measure unit used to measure it. Therefore, the measure unit of measurement is implicit in the logogram. If the amount of the commodity is lower than 1 unit, it is represented by one or more fraction signs placed directly after the logogram. You can see an example to the left on clay tablet Hania 11, where you see the logogram 303, which probably indicates cereal, possibly wheat or barley, directly followed by fraction signs. In that case, K, K plus L2, etc. If the amount is higher than 1 unit, but lower than 2 or more units, Fraction signs are placed after signs for whole numbers. You can see an example to the right on tablet Agia Triada 21, where, for example, we have the last entry, yes, the one pointed by Miguel, or the last entry, the logogram for olives, followed by 1 unit and fraction E. That means that the total amount is higher than 1, but lower than 2 units. This shows that the notation of fractions was cumulative and additive and in descending order, like the whole numbers we saw before, with the larger values written to the left or above the smaller. At times, fractions appear also ligature to commodity logograms, probably denoting fractions of the implicit unit of measurement. You see some examples on Khania 11, where, yes, exactly, logogram 303 is accompanied by fraction E, yes. Since linear A seems not to have had distinct signs for units of measurement, except for the heaviest weight, which had a specific sign, and on the ground of the comparison with other ancient and modern systems of measurement, we generally use different units according to the different nature of the commodities, especially dry and liquid commodities had different sets of units used for measuring them. It seems likely that the Minoan system also implied different units of measurement depending on the nature of products and implied to measure them. In this case, the absolute quantities measured would have changed, but not the relative mathematical value of the fraction signs used to point them out. This means that independently from the absolute amount recorded, the mathematical value of a given fraction signs remains the same. In the next slide, you can see the number of attestations of linear A fraction signs on their own as part of combinations and in ligature with logograms. Uncertain readings and attestations from that linear A inscriptions are excluded from this table. It should be stressed that the evidence at our disposal is not equally consistent for all sites and periods, and thus it is not possible to conduct a regional and diachronic development study aimed at reconstructing the development of the fraction system. We therefore focused on a specific set of linear A material, which is more largely distributed in the west, central, and eastern part of Crete, and dated to the late Minoan I period that approximately covers the 16th and the first half of the 15th century BC. This means that rare signs as epsilon and omega, which are so far only attested in the middle Minoan period, have been excluded from our analysis. We also excluded sign L as a self-standing value because it is only doubtfully attested on one middle Minoan document from Mallia and doubtfully on 3 late Minoan I documents shown in the next slide. You can appreciate, I think, how doubtful the identification of L is on the 2 documents called Khania 96, the above document, and Zakros 7, where the trace of the sign are so scanty, the evidence is too scanty to allow a secure reading of the sign here. We are left with only one possible attestation of L, but on a tablet from Zakros 11, where the sign L is joined to sign L2. This is in a very strange fashion, which will be further discussed and explained by Miguel. Moving on, for reasons of time, I will not discuss all previous suggestions put forward by other scholars, but this slide shows the most influential ones. They are mainly based on the interpretation of very difficult texts and rarely offer a solution for the whole system. So it is safe to say that the mathematical values of linear refractions is still a highly disputed topic. But why is it so difficult to deduce the mathematical values of these signs? The main problem is the bad status of preservation of the text. We do have some records of amounts of commodities, including whole numbers and fractions, which are totalized at the end, and which in theory would enable us to deduce mathematical values through an easy calculation. But unfortunately, no one of these is without reading or calculation problems. Here you see one of the most debated texts of this type that contains fraction signs of uncertain readings and miscalculations. Some scholars indeed used it to deduce the mathematical values of A, H, X, and L2. L2 is shown on the other side of the tablet. But both gaps and miscalculations on both the recto and the verso of the tablet strongly recommend avoiding building up hypotheses from such a text. However, the situation is not desperate. Thanks to the work carried out by Emmett Bennett, that is nowadays largely accepted, we can define the starting point of our work. First, Bennett suggested that most linear A fraction signs stood for fractions with numerator 1, like 1/2, 1/3, 1/4, etc., via a comparison with the contemporary Egyptian script. Moreover, he suggested the values of 3 signs through the frequency of the signs themselves and their combinations. With J as the most frequent sign, both per se in itself and as part of combinations, Bennett proposed its value to be 1/2. This value is also supported by the sum on clay tablet 104 from Aguia Triada, where we read 45, and then so we have different entries, now a list of recorded commodities. And if we read the numbers, we read 45, then plus 1 fraction J, then 20 plus another fraction J. Here the surface is damaged, but the diagnostic traits of J are still well recognizable, as I could check on the original tablet housed at the Archaeological Museum at Heraklion, and I would like to take the chance to acknowledge the archaeological museums of Heraklion and Hania for the permits to study and photograph these amazing materials. And the last entry counts for 29 units. At the end, we have a sum. The syllabic sequence scuro is interpreted as the Minoan word for total, because it matches with the sum of the entries which precede it. So that if we read the total 95, therefore, if 94 plus 2 sine J totals for 95, J is equal to 1/2. Should be 1/2. Furthermore, tablet 1 from Petras contains a proportion that also supports J equal to 1/2. As you can see, the logogram for personnel, the human figure, yes, here that Miguel is pointing to, is followed by numerals, and logogram 120, wheat or barley, ligatured with syllabogram pa, is followed by numerals too. This scheme is repeated twice on the tablet, and in the second entry, we have 72 people, followed by 36 units of grain of logogram 120. That means that each person is assigned half unit of grain. The same proportion appears in the first entry, where a certain number of people, we can read 5/10, where Miguel is pointing to, 5/10 followed by a gap. This registration is then followed by wheat, or the logogram for wheat or barley, for a total of 26 units and 1 fraction J. As suggested by the editors of this text, Metaxiatsipopoulou and Eric Gallagher, the damaged count of people is to be restored as double this amount, hence 53 people receiving 26 units and 1/2 of. Finally, Bennett also suggests that fraction E corresponds to 1/4, since E is the second most common fraction after J, and J is usually written above it or to its left, as shown in this slide. This means that E should be smaller than J, according to the descending order we mentioned before. On this slide, you see also a fragment, plaster fragment, where we have an interesting inscription incised on it. We find a sign number, the repetition of a sign number, conventionally numbered as 319, the one, yes, pointed by Miguel. And each of these signs is followed by numbers. So we have 1 plus fraction J, 2 plus fraction E, 3 plus fractions E and F. This has been interpreted by Pope as a geometric progression, where each value is the previous one multiplied by 1.5. Therefore, we obtain the progression 1, 1.5 with J equal to 1/2, 2.25 with E equal to 1/4, and 375 with F equal to 1/8. Then we have 2 damaged signs, which have been tentatively read as syllabograms, ta-ya, if we read them with linear B values, and then fraction K. This has been interpreted by Jean-Pierre Olivier as another step in the progression, that is 5 plus 1/16. According to this interpretation, K would be 1/16, but this implies the questionable assumption that 5 was phonetically spelled instead of being noted the same way as in all the other instances of whole numbers. So we do not accept this as a piece of evidence. Given the difficulties in deciphering the mathematical values of the linear fractions through the sole analysis of the text, we propose a constraint-based computational method for narrowing down their possible values that Miguel is going to explain. Thank you, Miguel.
Thank you, Barbara. So yes, moving on, what we did at this point was to look at all of the epigraphical data that the linear corpus provides us with and try to establish what we know the fraction signs can be and what they cannot be. And this can be summarized in 6 points. So first of all, based on what Barbara has just described, we set as we took for granted as correct the values proposed for J, E, and F. So 1/2, 1/4, and 1/8. As the second point, we noted that combinations of fractional signs are additive. So their value must be a combination of signs must contain an addition. As the third point, we assume that the system for notating fractions in linear A had to be practical and economical. This means that it had to have as few redundancies as possible. So one value should not be represented by more than one sign of the 17 that we have, and one value should not be represented by both a sign and a combination of signs. One implication of this, for example, was that unlike Egyptian, linear A shouldn't have a sign for 3/4 because the combination GE would already express this, so that if you have a half plus 1/4, it equals 3/4, and it is written with a combination. As a fourth point in terms of constraints, we know that any fraction sign or sum of combined signs has to be less than 1, because as Barbara explained, once you reach 1, and after that, the Minoans used signs for whole numbers. So for example, if you wanted to write 5.75, so 5 plus 3/4, you would write 5 with 5 vertical strokes for units, and then you'd use signs for J and E as shown in this example. There are some exceptions to this, very few, but they are all from an early period and from Festos. In particular, they come from Middle Minoan 2 documents, so the very early days of linear A. And what we have are a couple of examples of JJ, so half and half, being written cumulatively instead of being replaced by 1. And likewise, what appears to be EE, so 1/4 and 1/4, being written cumulatively instead of being replaced by J for a half. But since these examples are not part of our late Minoan 1 synchronic corpus in system of fractions, we did not take it into account because during the late Minoan 1, we see that scribes do not appear to be writing cumulatively in this way. So then the fifth point is that, again, as Barbara explained, any fraction is higher than the fraction placed to the right or below it. So J is higher than E. Overall, what this gives us is a sort of a chain in which we know the relative values of a number of signs. So in this chain, we know that J is higher than E, E should be higher than F should be higher than K, and so forth down to L4 here. And then we have similar minimal information for 3 or 4 more signs, but we do not have information enough to make them fit within the same chain I have just described. So we just know that J is higher than A, J is higher than H, and E is higher than B, but we cannot place A, B, and H within this chain for lack of evidence. Then we have the situation with that very curious merged semicircular shape with L2, which in theory would tell us that an L shape would represent a value higher than L2, but this is problematic, as we will see. As a final point, we have the L series, which seems to be mechanically designed. That is, what we see is the same basic shape as described by Barbara again. So a semicircle or a triangle to which strokes or dots are added. And the way this series is devised suggests that the signs are interrelated and that the strokes or dots divide, or better, sorry, the strokes or dots somehow modify a value L represented by the basic shape. Now, our assumption is that this series has to be divisive. And why is this? Because it seems impossible that the strokes are multiplying or adding something. Because if they were, for example, L4 would be higher than L2. But this violates the constraint 5 that we saw before, which is we find that L4 is written to the right of L2, so it should have a lower value. Likewise, it seems impossible that the strokes subtract, because if the strokes subtracted, we would end up with negative values. So we are left with division, and division as the relationship that lies underneath this series makes sense, because division is precisely the operation of fractioning, the operation that goes on when you fraction something, a unit, for example. But once we take this premise that the L series is divisive, what kind of division does it entail? And we saw two possibilities. According to one of them, each stroke would divide L by 10, so that, for example, L2 would be L, whatever L is, divided by 20. L3 would be L divided by 30, and so forth. According to option 2, the stroke would be a unit, so it would divide 1, and L2 would be L, again, whatever L is, divided by 2. L3 would be L divided by 3, and so forth. And this would, of course, make a sort of progression, a divisible relationship. We favored option 2 because it fit the systemic evidence, so to speak, that we have. Because we do not observe a semicircular or triangular shape with one stroke. In other words, we don't have attested L1. And this, it seems unlikely that this is an accident of preservation, because if you remember the table that Barbara showed before, and we'll see this again in a few minutes, we know that L2 is has more attestations than L3. L3 has more attestations than L4, and so forth. In other words, if L1 existed, we would expect it to be more frequent than L2 and not attested. So the fact that we lack L1 fits with option 2, because in it, L1 would be L divided by 1, so L would equal itself, and it would make no sense to have an L and an L1. So we chose this option as a constraint. And what we did next was to represent all of these 6 constraints in a mathematical form and used software to process it. And this part will be explained to you by Michele, our colleague Michele Corazza.
Thank you, Miguel. So instead of just saying that we encoded constraints in a constraint programming system and the system worked, we thought it would be best to give you a brief example, a toy example, let's say, of how you encode a program with this paradigm. So if we look at the top part of this slide, what we can see is that the first step is defining the variables, which in this case are X, Y, and Z. And here already a crucial aspect of this approach is evident, because that 1.4 is basically the range of values that these variables can take. This is important because in constraint programming, you cannot, of course, have infinite ranges, because that would lead very often to an infinite number of solutions, which cannot be computed by a machine. But also because the amount of values that you choose will influence the number of solutions that you will have. So this is a crucial aspect that Miguel will discuss in detail later with regards to the fractions. Then we have a couple of constraints that give us an ordering. And so we know that X is less than Y and that Y is less than Z. This is analogous to what we have in the fraction system, as we saw that they appear in decreasing order in the documents. Finally, we have another constraint over a sum. So we know that X plus Y is less than Z. This in a way is analogous to another constraint that we discussed before, which is the fact that every combination of fractions must have a value which is less than 1. So also for fractions, we have this kind of constraint. Finally, we tell the system to solve satisfy, which in this case is simply stating that we are not interested in specific properties of the solutions, but we want all values, all assignments that satisfy these constraints. So if you look at the bottom of the slide here, you can see that in this very simple example, there is only one possible solution. However, this is of course not the case for the fractions, because it is an under constraint problem. In other words, the constraints that we have are not enough to find a unique solutions that fits them. And with that, I will pass the ball back to Miguel.
Thank you, Michele. So based on what Michele just explained, the challenge we faced was that to have many possible values meant more computation time, and it would hinder a bit the research. And we had to face this issue. But the fact is that for everyone, even at let's say an intuitive level, it would be clear that not any kind of value would make sense for a linear fraction. So for example, I think very few scholars would expect one of the signs to have a value like 1/375, for example. So it was more or less obvious that values like this could be excluded from the computation. But at the same time, we did not want to exclude too much and risk biasing our results, introducing a bias to our results. So we had to find a way to limit the possible values in a way that was reasonable and could be argued without, again, generating a bias. So we did three things in terms of limiting the possible values. The first thing was to follow Bennett's assumption, which is true. Any system of fraction will tend to have most mathematical values being of numerator 1. So we established a range from the highest fraction possible, a half, down to 1n, and being the lowest denominator or the highest denominator possible in a system. Then we had to exclude, as I said, implausible values within this range. I will explain how we did this in a minute. And at the same time, we had to include some possible values with numerators other than 1, because historically these are attested. So the solution to do this in a reasoned way became clear when we thought about these three principles, because it became clear that it was important to look at the way in which fractions have been notated throughout history in the world. So the solution was to look at typology and see if there were patterns and things that make sense in terms of fraction systems. The first important point is that if you remember what the system of fractions of linear A looks like, the one we saw at the beginning of the talk, it should be more or less clear that the signs, the symbols, are not related to the shapes of the symbols for whole numbers in linear A. The only possible exception is the L series, where the horizontal strokes or dots might be somehow related to the signs representing the tens. But other than that, linear A uses special symbols to denote fractions. This is unlike, for example, our own modern notation, where what we do is, if we want to write, for example, a half, we use the integers or the whole number digits. So we use digit 1 and we use digit 2, and we use a slash to indicate the fractioning or the division. So our notation for fractions is basically based on the shapes of signs for whole numbers. Conversely, we found 10 systems that mostly from ancient times, but all around the world. Well, actually, sorry. Most of them from in or around the Eastern Mediterranean and from India. We found 10 systems that did this. Even if the notation of fractions included signs based on the integers for some values, at least some, in these cases, were represented by special symbols, special shapes unrelated to the integers. So we have, in our survey, we found 4 Egyptian systems. We found 2 alphabetical systems, Greek alphabetical and Coptic alphabetical, 2, so to speak, Arabic systems, Rumi and Vulgar Arabic, the cuneiform one from the Old Akkadian and Old Babylonian periods, and the Granta system from India. One of the Egyptian systems is actually very specialized sets with no signs whatsoever based on whole number shapes and forms a binary or base 2 system of values. As you can see easily, there are values that repeat a lot and instances that they do, such as half, for example. And then there were other kinds of tendencies. For example, an interesting one, as we will see, is the fact that we don't see for 1/6 present unless it also has a special notation for 2/3 and 1/3. Now, so what we did first was to possible in the sense of typologically attested values and include them as possibilities for our linear fractions. And the lowest of these, which is found in the Granta system, would be 1/320. However, it seemed very restrictive and dangerous even to use just these values as possibilities. But it became difficult to exclude values with good reason. So what we thought was sensible was to look at not just fraction sign, numerical notations for whole numbers worldwide, which we could do thanks to the amazing work by Chrysomalis 2010, which is a compilation of numerical notations from all around the world and all eras. And we realized that, as most people will probably know, most of them are function on a decimal basis, but we also find numerical notations that contain values from subbases 2 and 5. We have sexagesimal systems, so and so forth. So what we did was we included values of 10, one fraction we have attested typologically. We included multiples of 12 up to 120, and we also included two fractional values with odd numbers, 1/7 and 1/9, because these had been proposed by Shriver 2014 for sign D. So this yielded this group of values here. And in case some of you are wondering whether this might be too restrictive, whether there might be fractions in the world unattested so far, or even if there aren't, maybe the linear fractions have values smaller than 1/320. This didn't feel very restrictive because for signs like A, B, D, H, and K, which are the ones we were applying these possible values to, it felt unlikely that they had such a small denominator. And why? Well, the case of sign D, it is the third most frequent sign. So based on the principle that Bennett came up with in the 50s, D should be a relatively high fraction. Likewise, fractions A, B, H, and K combine with J, which is a half. And it doesn't seem likely that the Minoans would be combining fractions with denominators that were very, very different. So it doesn't seem likely that a J, a half, would be combined with a sign for 1/1000 and something, for example. And as an illustration of this, even if our lowest fraction, according to the constraints, L6, was 1/320, then, for example, L2, which is attested 26 times, would be something like 1, or rather, could not be lower than 1/107. So with all of these pieces of evidence, it didn't seem too restrictive to set this limit. However, for the signs in the L series, we were even less restrictive because we observed that thanks to constraint 1, the L series had to be lower than 1/8, because if F is 1/8 and the signs in the L series are lower than it, they have to be 1/9 or lower. And this means that when we look at the divisive relationship of the L series, we find a and historically attested systems of fractions which have values lower than 1/9. In other words, if you go to the Iavoras system from Egypt or the Granta system from India, and you look at the values lower than 1/9, you will not find values that match this progression. So we had to be cautious. And for the L series, we allowed every value between 1/2 and 1/320. But then the big issue was what to do with the supposed L shape, which, for example, in the standard corpus of linear array was considered a possible, an entity, a sign within the fraction systems of linear array. As Barbara showed, all of its attestations in the late Minoan period are doubtful, and perhaps the only one that seems possible is this one here from tablet Zachros 11, where supposedly we have L, L2, but it is very strange because we find the two shapes, the one that would supposedly be L and L2 merged together, fused together, and this is something we don't see with the rest of the fractions and the rest of the corpus. So it would be a sign with frequency 1, and it would be very strange. So we wanted to address this problem and feel safe about excluding it from our system and our approach. So we turned our attention to that principle laid down by Bennett in 1950, that the higher a linear refraction, the more frequent it should be. And this principle it makes sense, it seems to make sense, but it was not clear why it should be so. So we tried to investigate what was the mathematical principle behind it. And we concluded that this was based on a certain correlation between the number of common divisors of a fraction sign and the frequency of that same fraction sign. This gets a bit technical, but let's try to exemplify it. So imagine you have a system of fractions that functions like linear array. So this means that if you have a special sign for 1/2 and you have a special sign for 1/4, two signs for 1/4, that is 2/4, will equal 1/2. So you can replace those by the sign for 1/2. And this is what we see, except for those possible exceptions in the middle Minoan 2 period, you don't see EE. You don't see 1/4, 1/4. It gets replaced by J. So this replacement rule means that even if in your economy, you are not operating with 1/2 as a measure of something very often, you will still need to use the sign for 1/2 very often because of this principle. Because anytime you need to write 1/2 plus something, you will potentially write it with J plus one or more signs. So as an example, if you have 1/4, 1/4, and 1/4, 3/4, you do what we have seen before. You replace 2/4 with J, and then you had only one E, and you get JE. If you think of this in terms of a system, what this means is that the smaller the denominator of a fraction, the more frequent its sign will be. And the higher the denominator of a fraction, the less frequent a sign will be. And even with only the three starting values we have from the investigations of Bennett and Pope, we already see that work. That J is the most frequent fraction, both by itself and in combination. The second most frequent is E, and this squares well with the values they have. So let's think of a fictitious system where you have J for 1/2, E for 1/4, and F for 1/8, as we do have, and then signs, which we don't know which signs those would be yet. Then we have signs for 1/3, 1/5, 1/6, 1/10, and 1/20. In this system, 1, 2, 3, 4, 5 signs will have common divisors in common with J. So J has 5 common divisors, and E will have 1, 2, 3 signs with common divisors. So again, J has more common divisors than E, and J appears as more frequent than E. This doesn't need to be an absolute rule, but there should definitely, if this principle is to work, there should definitely be a certain rank correlation in terms of how many common divisors a sign will have and how frequent it will be. And then we see why this implies that L is not really a sign and less so a sign that operates with the L series. Because within the L series, well, yes, according to our constraints, the higher value the sign has, the more frequent it is, with L2 having 26 attestations. And if L were really a sign and higher than L2, as we would observe in the Zachros tablet, then we would expect it to be at least as frequent, if not more frequent than L2. And this principle is important also for something else, because since the Minoans did not have a system for notating fractions like ours, we need to think of the way in which they would compute their fractions and come to figure out which combination they would need to write to represent a specific value. And if they thought in terms of common divisors, this would probably make things easier for them. So if we look at this hypothetical example, if you have 11/20, you would not write it with 11 signs for 1/20, because this would make for a very cumbersome and impractical system. Rather, what you would do is you would know that once you have 10/20, it's the same as having a half. So it's the same as having J. So you do a replacement. You would replace 10 of these signs by just 1 for J, and then you write one more for 1/20. So you would write this with 2 signs. And we might even wonder if the Minoan scribes didn't keep a table of equivalences of some sort as a reference for doing this. And it doesn't seem like something very far-fetched, seeing that they wrote graffiti such as the one showed by Barbara with arithmetical progressions. Now, again, to feel safe about excluding the L, what we did was to run a first simulation with the constant programming and see what systems the software gave us as solutions. And there were many. I believe there were about 2 million in this first simulation. And we'll look at some random systems, a number of them. And what we saw was that, as expected, consistently, the number of common divisors for an L sign that would be part of the L series was much higher than that expected for a sign with frequency of 1. In other words, we would expect it actually to be further up here in this table, around the same height or even in a higher position than L2. And this was not the case. And this was a very strong mathematical indication that the L was not an entity in the late Minoan period, because it didn't respect the correlation. Whereas the results would respect the correlation if L would be excluded. We did yet a second test because we wanted to see, considering the relationship of the L series and the frequency of signs in the L series, we ran a Pearson's chi-square goodness of fitness statistical test to see how probable it would be to have L with frequency 1 in a system with this correlation between divisors and the frequency of signs. And the fact is that the results indicate that the probability is really too low. And it's so low that it cannot be due to chance. So finally, after these 2 tests, we felt confident enough to exclude L and run a new simulation where L would not be a sign part of the system. And with this, I now pass the word again to Michele.
Thank you, Miguel. So as Miguel said, once we apply the constraints that he discussed previously, we still have a big problem because the problem is severely under constraint, and therefore even after excluding the L, we have almost 4 million solutions. Therefore, we need an automatic way to filter them out that is as objective as possible and that captures what we would like to see in an hypothetical best solution. Therefore, we devised 4 ad hoc metrics, which I will now describe. So first of all, we have the frequency of a sign versus the number of its divisor in the fraction system. This relates, of course, to what was said previously, so I will not discuss it further. Then we have a measure of ambiguity of the system. This measures the number of cases where we have 2 attested combinations of signs that yield the same value. One might ask why this is not a constraint, right? Why do we allow some ambiguous combination? And this is because we felt that this was too strict of a criteria, because once you introduce a lot of signs, it's easier to build combinations that have some form of ambiguity. So we still consider it a good indicator of a good solution, but it is not a hard, if you have ambiguity, we cut off we cut off this solution. In addition to this, we had also a typological based metric, which measure the number of attested fraction values that are typologically attested in other systems throughout history. Again, this is not a hard constraint, but we feel like there is a pattern to be seen with the historically attested fraction values, and therefore we expect them. We expect linear array to show many values that are often attested in fraction systems. Finally, we have an optimality measure that measures how many values in the fractional range of the solution can be represented. What do I mean with the fractional range? Basically, we take from 1/2 to 1 over the biggest denominator of the system, and we see how many of those values can be represented by a combination of at most 4 signs. The choice of 4 signs is based on the fact that we find at most combinations of 4 fraction signs in linear array. So in the next slide, we discuss a big problem that we have, which is the fact that when computing G-optimal, we of course have to calculate every possible combination of signs of 4 or less signs. When you think that this would need to be applied to almost 4 million solutions, you can see that this becomes very computationally expensive. Therefore, we decided to apply the first 3 metrics first, so to exclude initially the optimality metric, and to use their product to produce the best 5,000 solutions. Then once we reduced the number of solutions, we could then apply G-optimal to obtain a ranking and see which ones were the best. We then examined the best solutions that we obtained with this procedure, and we noticed that in terms of the optimality metric, we had the following assignment in the 48 best solutions. So K is equal to 1/10, L2 is equal to 1/20, L3 is equal to 1/30, and so on. So these assignments would yield a decimal sexagesimal system for L, and the fact that they appear so prominently in the most optimal solutions implies that they are the assignment that are better at expressing value within the system fractional based. So in a nutshell, they are very useful that already knew. We then selected the 100 solutions with this assignment and moved on with our investigation. In 86 of the 100 remaining solutions, we saw the assignments of B equal to 1/5 and D equal to 1/6. And these assignments appeared in the 28 most optimal solutions. So we can say for sure that this assignment ranked better and more consistently than any alternative, and lead to fewer unattested values in many denominator and numeric fraction ranges, let's call them. In addition, another property of D is the fact that D appears in combination with itself repeated 2 and 4 times, but never 3. So if we suppose that D is 1/6, we would have the missing triple repetition, so DDD, would be equal to 3/6. Therefore, it would be 1/2, which we already know it is J. So this fits very well with what we know already. Additionally, we would see that DD and DDDD would be used to express 1/3 and 2/3. And if you remember from what Miguel said earlier, we know that every system, every fraction system that has 1/6 also has a way to represent 1/3 and 2/3. So this is also further evidence. Finally, if we are discussing the value of B, so 1/5, 1/5, we would expect this value to be frequently attested in combinations when you have a decimal sexagesimal system or a decimal sexagesimal subcomponent of the system. And having 5 as a kind of sub-base for 10 would make a lot of sense. In the 28 remaining solution, H and A can have a lot of values. What we observed is that in terms of optimality, there is no clear pattern that can tell us which value is the best in terms of optimality. However, here we can use another consideration, which is the fact that H might share a modified version of the crooked shape, which is present in J, E, F, and H. And we know that J is 1/2, E is 1/4, and F is 1/8. So this would suggest a kind of base 2 progression where H is equal to 1/16, which coincidentally is also the only possible value for H, which is not possible for A. Next, we discuss the value of A. If we assign H to 1/16, the only thinking about the optimality alone, we would see that the best assignment for A is 1/36. However, this changes a lot if we consider the hypothesis that X is just another way of writing AA. So in this case, we would have A, if A is equal to 1/24, then X would be 1/12. And they both would be a very good fit for a fraction system with a decimal sexagesimal component, as we discussed before. And as 12 is a divisor on 240, and so is 24. So basically, they would be very useful in combination in such a system. Finally, here we have a final slide that shows all the assignments and the value assignment that we propose. And in particular, we need to underline the fact that for A, X, W, and also for H, the values have a question mark because they are more tentative than the rest. Why? Because they do not derive directly from our metrics, but they require additional considerations in order to emerge from the possible solutions. In addition, I highlighted in bold the value assignment that were not proposed previously in structure. In addition, so in conclusion, if we following our reasoning about the constraints and the value choices and the choice of metrics to decide which system is the best, we can say that this system, minus to an extent the more tentative assignments, is surely the one that is better at in terms of ambiguity, in terms of optimality, in terms of frequency and divisors. But there is also another property of this system, which Barbara will now discuss.
Thanks, Michele. I would like to conclude this talk, this presentation, by showing the historical implications of the proposal. Indeed, our optimal system of linear A fraction values reveals possible relationships with the linear B signs for measurements. As I said at the beginning of this talk, linear B writing system was adapted from linear A. But between the two, there is a significant difference. The record commodities of quantities of commodities differently. Linear B employs no numerical fractions, but rather three special sets of logograms, which stood for units of dry and liquid commodities and weights. You can see them here on this slide. Like a linear A, the measure unit is implicit in the logograms for dry and liquid commodities. But unlike linear A, subunits are noted through special signs placed between the logogram, so the commodity logogram, and the numerical phrase. If the commodities are weighed, as for example in case of metals, linear B scribes use the same special sign for the heaviest weight, also used in linear A, sign 118. I will try to avoid calling Mycenaean units of measurement with true capital letters, which is another way to transcribe them in order to not to create confusion between linear B unit of measurements and linear A fractions. So wall was also weighed, but its logogram called Lana, or called logogram 145, that originally was a monogram. The logogram implies the specific weight used to weigh. The ratio between logogram Lana and the heaviest weight, represented by the sign conventionally numbered as 118, is 1/10, 1/10. Lighter weight 117 is equal to 1/30 of the heaviest weight and to 1/3 of Lana, while the even lighter weight, sign 116, is equal to 1/120 of the highest unit of the heaviest weight and to 1/12 of Lana, of logogram for wall. Let's now consider that the two linear B signs for weights we have just mentioned, namely 117 and 116, and two signs for subunits used to measure dry commodities have the same shape as linear A fractions. This suggests that these linear B signs were adapted from the linear A fraction signs. And even though the two systems registered quantities differently, the linear B system took inspiration from linear A. Indeed, as you can see on this slide, the shape of the linear A combination DD, whose suggested value is 1/3, is identical to linear B sign 117, which represents 1/3 of the largest weight measure for wall. The shape of linear A X, so the fraction X, most probably equal to AA, that is 1/12, is identical to linear B sign 116, which represents 1/12 of the largest weight measure for wall. The shape of fraction K, whose suggested value is 1/10, is identical to linear B sign 112, which represents 1/10 of the largest dry capacity measure. Finally, the shape contained in the linear A decimal sexagesimal L series linear B sine 111, which represents 1/60 of the largest dry capacity measure. Let's now try to imagine how the adaptation may have taken place. Measures were implicit in linear A commodities logogram, so were implicit in both linear A and linear B commodity logograms, and some of them in linear A were ligatured with fractional signs. For example, the ligature between the logogram 303, yes, this one, and fraction D, which is on the yes, exactly, you can see there, most probably meant roughly 1/3 of the serial measure. Some fractional signs in time were interpreted to note a certain part of a measure. Moreover, the frequent use of the combination of two fractions, fraction K and fraction L2, as a measure for serial. You see here to the right 3 examples on the same tablet. Logogram 303, wheat or barley, followed by fraction K and fraction D and fraction L2, sorry. This gives some support to the notion that the sign shapes of K and L series became associated with dry capacity measures, and the creators of linear B may have reused them as such. Thus, we can observe a redeployment of Saminoa fractions in the Mycenaean measuring system. The results achieved by applying a multi-stranded paleographical, typological, computational, and statistical method converge therefore in a coherent and systematic fashion, which also contribute to shed light on the passage from the linear A fraction system to the linear B metrical system. Thank you very much for your attention from all of us.
Thank you, Barbara. Thank you, Miguel. Thank you, Michele. Thank you, Fabio Tamburini, who's showing a big smile in that last image. I really enjoyed this ping-ponging of inscribers. And of course, you're kind of preaching to the converted when it comes to me being a co-author. So I would like to open the floor for any questions that you may have. You can raise your hand and unmute yourself and ask the question directly. I may ask a question later on. Anybody that wants to break the ice? Technical presentation, of course, quite difficult. I hope you managed to follow all the intricacies and details. No questions? I'll ask my question. Of course, we had some problems defining the denominator. To what extent can we extend the denominator? Is typology strong enough for us to go by? And that L business was really breaking our brains, like, you know, racking our brains to desperation at times. But well, my question is pretty much, you know, having tried to overcome all of these difficulties and obstacles, is there any room for error? I mean, we are proposing some definitive values. We're also postulating a couple, but is there room for error in the whole methodology? Is this foolproof? Because of course, you know, this is the devil's advocate question when it comes to methodology, right?
Yeah.
Who wants to answer?
Can I go? Do you want to go?
You go,
please, Miguel.
Miguel.
I will. That question, I would just answer what Barbara was conveying at the end, along with Michele, and what we wrote in the paper, which is that we did our best with the current evidence, and what we try to formulate our results in terms of a hypothesis, which is that given the current data, the constraints we can extract from the data, from the linear A fractions, if the linear A system of fractions in the late mid in the late Minoan 1 period was a practical, economical system, optimal system that was as little redundant as possible and respected what we know from the typology of notations of fractions, then these values ought to be correct, minus the more tentative ones. Of course, in our business, it all ultimately depends on the tablet that may come out tomorrow, I would say.
Mm-hmm.
So we will be expecting to see if an L comes up one day, or and which would prove us wrong, or whether some new tablet will contain a sum that will show that some of the values that we have proposed and had not been so far are correct.
Yes, I was going to say the same concept, express the same concept, meaning that I think that only new evidence, new possible evidence coming to light in the next years could definitely prove or improve or disprove our proposal. A definitive proof, it is not at our disposal yet, I think. Because of the scanty evidence, above all for fractions like A, X, which are so scarcely attested.
Yes, of course, those were a big obstacle into reaching a coherent picture. But the coherent picture really emerges when you look at the linear B value signs for the measurements, which tie up quite nicely. So, and of course, we didn't go by sort of an ex post, as it were, methodology whereby we use those. We ended up reaching this, converging with the values of the measurements in the linear B as a result of all that constraints, that constraint programming and typological analysis and structural analysis. Michele, do you want to add anything to this?
What I can add is that the criteria we used were as objective as possible, right? And the fact that we use a very, how can you say, strict methodology of applying constraints and then varying by metrics and then applying another metric on top of those makes these results stronger. Of course, the results, as Miguel and Barbara said, they are as strong as the data and that they are based on, right? So it's not like if we could prove the values, I think people would have done it by hand already. So there is a possibility that some of it is proven wrong, but at the same time, the overall picture seems very coherent. And as a non-expert, they do look to be correct.
But of course, you're an expert in other things such as computer science, neural networks as such. To what extent? I mean, there are loads of naysayers that think that methodologies that have to do with computational strategies are fraught when it comes to dealing with scanty material, with a dearth of data. To what extent do you think that such a method, of course, tweaking it to different problems, can be applied in order to understand undeciphered scripts? That's a question to you specifically, out of turn when it comes to computer science and the intricacies of deep neural networks. And perhaps Fabio can join in with this if he wants to.
So, of course, I think that they can be applied. Otherwise, my PhD would be over and I would need to look for a new job. But for me, it's very different from this, right? Because constraint programming is logical in nature in a way. So given the constraints, the system will tell you something, and that something is by definition correct. It will not get the constraint wrong. So if you see a solution, it means that the constraints are satisfied, full stop. Right? With neural networks, you have the problem that they are not 100% accurate. So you need to in my opinion, find ways to mitigate the inaccuracies that you see in the results and try to perhaps interpret overall trends instead of trying to classify everything on a very fine-grained level, because otherwise you're stuck with the noise that is inherent in this kind of methods, and that is also inherent in every human artifact, in language, in even pictures or I don't know, paintings or whatever you can imagine has some form of noise that is into it. And the problem is that these methods sometimes overinterpret this kind of noise, or conversely, they are not able to distinguish the signal from the noise. So that, of course, makes things more difficult.
Yes, and every undeciphered writing system has its own personality and idiosyncrasies and bad character, you know, so one needs to tackle it applying an ad hoc kind of system that will bring to light new evidence. And we are seeing this with the Cyprian script and trying to apply whatever it is that you're applying. Michele, you can talk about it if you want, of course. But we see how difficult it is to spot the different graphic shapes through the computer. That is one of the main issues at hand when it comes to unsupervised methods, right?
Yeah, but even with supervised methods, unfortunately, we are not, it's very, if I see, let me put it that way, if I see a paper that claims 100% accuracy, and you never see them, by the way, I think that there is something wrong. I don't think that they discovered, I mean, it might happen, but so far it's more difficult than that.
But this is why computers need to be guided. You can't detract from the equation the sort of paleographical eye. And this could not have been done without Barbara and Miguel having the input when it comes to paleography and typology, right? So that is a concerted effort, a synergy of methods, of strategies that worked and converged towards the same end. And hopefully that can be done for other writing systems. I'm thinking of Rongo Rongo from Easter Island. Perhaps that could be tackled using neural networks, but we'll talk about it soon, hopefully.
I think it won't be too anthropocentric to say that Michele was hinting at this. It's not that there is an inherent problem with any computational method. It's just that the method is only as good as the data you feed it with and the human choices and the questions asked. That's where I think that's where the concern of possible naysayers would come.
Yes. There is a comment and a question in the chat from Laura Winters. Because the forms are so similar, the A and B signs, 1/24 and 1/5, look as though they ought to be related in some way, reciprocal, etc. Is there a possible value set for those signs that would make them more closely related than 1/24 and 1/5? Or is the similarity of the symbols only a coincidence?
No, I would say that we also wondered we asked them ourselves the same question while we were working on the wall system and the wall shapes, and we also noticed the similarity in shapes. But correct me, Michele and Miguel, if I'm wrong, but we tried to find out other possibilities which took into consideration the similar shapes, but the result was negative. So indeed, we took this into consideration. If you have anything to add,
no, this refers to that stage of the metrics when we were filtering results, where we had to deal with the values for age and A. And because optimality was not helping, so yeah, the result was negative in the sense that assigning a value to A that was somehow related to B and 1/5 didn't seem possible. But I think that the main thing to take into consideration here is that we have a lot of discussions, and we discuss a lot about the shapes and how they might be interrelated. And for example, I was wondering, you might look at it from another perspective, and you might say, oh, maybe K, which is 1/10, is just half of B. It's B cut in two, so that there you go, another relationship. But we try to, I think it's fair to say that we try to stay away from this kind of reasoning and focused on the method and the metrics and optimality, and instead of purposefully feeding us previous assumptions or prior assumptions about what the shapes might represent to the solution.
I would also add, this is
You're welcome.
just how to say, a marginal observation, not anything definitive or proving. But we also observe that the same shapes used for A, fraction A and B are shapes used for syllabic signs, which are different. So we could imagine that these two shapes were conceptualized in a different way. So they were created in a non-mechanical way. By contrast, the shape of sign X is not used for, doesn't look like a shape for a phonetic sign. So it might be mechanically derived from sign B, from sign A. So yeah, B is the cross and A, sorry.
Okay, do we have any more live questions? Fabio, come on, say something. There is somebody who's clapping. I want to say hi to Fabio, who very kindly joined us. We know he's very busy.
Hi.
Ciao, Fabio.
Ciao.
Esther Salgarella, you can unmute yourself. Oh, there's Toma as well. Shall we, ladies first? Esther, hi.
Hi, everybody. Sorry, I wasn't able to put the question hand on. So first of all, I'd like to congratulate you on a very cutting-edge piece of research. It is really amazing work, and I'm really impressed by what you have achieved. So I think my question has got more to do with the tools in general. So I was wondering whether you thought about the wider implication of this research in relation to the potential identification of linear A, especially the unidentified linear A commodities. And this is mostly based on your results on the numerical combinations. So I don't know, have you got any idea about which kind of implication you can have?
Wow, that is a big one. That's a biggie.
I'm just wondering, because all the research that has been carried out on linear B based on fractional values, so food rations, allocation, and all this stuff. So I was wondering whether maybe this kind of research could be pushed a step further by looking at the still unidentified linear A, so-called logograms or composite signs, to try and come to some identification.
That is spot on, Esther. Thank you so much. A big one, huh? Barbara or Miguel?
No, I would say that thank you, Esther, for this insightful question. It is a big question. Yes, I think that we could try to investigate further the relationship between certain commodities and certain amounts recorded in linear B records, and certain commodities possibly linked preference with certain fraction signs, and see if we can find out a pattern or a correspondence in the quantities recorded. I think that this actually, for the use of the value we suggest for fraction D and DD fits well with what we know about the relations delivered and recorded in linear B.
Well, I think we can safely say that the system lasted after the eruption, right? And it even got, or so we tried to propose in this presentation, it got adapted in a way by the users and the divisors of the linear B writing system. What I didn't fully get, and that I apologize for it, is the last part of your question. When you were mentioning what it meant for the system in terms of being used by the Minoans, did I understand correctly?
From the Minoans, how did this numeral system and fraction system transitioned into cultures post-Minoan?
Mhm.
And if evidence of how the numeral system was used after the Minoan time, would that help validate how it was understood? And are there some more examples that you could look at that would help validate the numeral system that you've put together?
Well, I can maybe provide one or two data that might help address those issues, and then my colleagues can step in and correct me or add to what I say. I don't think there is any, not known to me, there is any trace of this system being borrowed or influencing any others after linear A or linear B became obsolete. An interesting datum is that most of the systems that we showed in our survey, which contain fraction signs, which are special shapes and related to the whole numbers, are in areas in and around Egypt. And curiously, it was argued by Stefan Chrysomalis in, I think, a 2003 paper that the Greek alphabetical system of fractions was conceptually influenced by the Egyptian one. So if you think of Greek as something that was used in the Aegean territory, so if you think of the Greek alphabetical system of fractions in the first millennium, I think BCE, as something used in the Aegean territory after the Minoan and the Mycenaean times, that one doesn't seem to be influenced by the Minoan one, but rather by the Egyptian one. And I think that's as much as I can say without speculating too much.
Okay, I'm also interested in looking at if there was any reach from the Minoans. I'm in particular interested if the Persians had an understanding or grasp of the Minoan usage of the numbers.
Well, if you mean people in the area of Iran at about the same time, I wouldn't know. Not that it is known to me.
You mean in Elamite, Thomas?
Sure, that's kind of where I'm looking at.
I wouldn't know how to answer that question.
Not as far as I know. We are talking about peoples in the so-called, well, in the orbit of the cuneiform world. So as far as I know, that is what they would be using at around the same time.
But we didn't use that in our typological analysis.
Okay, so there's very scant evidence that the system influenced any other areas outside of the Aegean.
Yes.
Yeah, that's for sure.
Thank you.
Okay. Is there any more from the audience? Any comments, any ideas, any suggestion?
It's not a question nor a suggestion. I would like, I'm not an expert in this aspects of ancient writing system analysis, like numerical notation, but I think that this pioneering study conducted in such a way, with such innovative approach, combining different expertises and methodologies can be revolutionary, truly revolutionary, both for its absolute results and for the implications it has in the issue of the adaptation of linear A to linear B sign, linear A signs to linear B. So I can only congratulate the SCRIBO team and thank you all for this incredibly stimulating series of seminars. Thank you all.
Professor Matilde
Matilde.
Civitillo did not receive a commission to say this.
Grazie a voi.
My connection is so poor. I'm going to say goodbye. Thank you everybody for being here. Thank you everybody for having joined us and having followed this and having followed the whole series. It's bye-bye again. And thank you, Matilde. Thank you, Fabio. Thank you, Barbara, Michele, Miguel, everybody. Thank you. Bye-bye.